In the last video, we worked out that for single slit diffraction, where we had a long thin slit, the location of the diffraction minima were directly proportional to the wavelength of the light and inversely proportional to the thickness of the slit. Now in this situation here, even though the figure is going to look the same, what I'm imagining here now is that this is a circular aperture. That we are looking at in cross section, and we will say that the diameter of it is d. If I go project out onto a screen, it'll still be the case that we will end up having some sort of a central maximum with successive minima. And if I were to look at this more edge on here, I would see a bright region in the middle, a dimmer ring around it, a dimmer ring around it like that, with dark interference bands. In between. And locating where each of these minima are is beyond the scope of this treatment. But to locate the first one, I will just assert that using a similar analysis, but unfortunately invoking a lot more calculus, this angle here, assuming it's small, and it almost always is, will be equal to 1.22 lambda over d. Unfortunately, you can't say that the second minimum is located at 2.44 or anything like that. The numbers are nowhere near as kind as that. But the first minimum is located out at 1.22 lambda over d. And as a practical matter, in circular aperture diffraction, the central maximum is a lot brighter than any of the other rings around it. Okay. So this has some application to looking at lenses and mirrors. Earlier, when I'd looked at lenses and mirrors, let's just take a look at a lens. Same kind of thing happens for a mirror. So let's say I have a lens. The lens itself here is acting as a circular aperture. So what this means is, in addition to looking at the rays going into a focus, we have to take into account that there will be circular diffraction occurring, and that what this means is that it won't all come to a single point. We can roughly ballpark it out. If this is a plane wave going in, if this lens were infinitely wide, it would come to a focus out at a focal length of f. But now we're going to be saying, well, it's actually going to split off just a little bit to the tune of up and down by this angle theta that we had just calculated, equal to 1.22 lambda over d, where d here would be the diameter of my lens. So that means this entire angle here would be 2 theta. So if I'm trying to guess how wide of a spot I could possibly come to a focus at, this width of the spot, the tightest focus I can possibly get, that would be roughly 2 theta times the focal length. Because the angles are small, we can approximate it that way. So if theta is 1.22 lambda over d, that means that the width of my spot would be about 2.44 lambda f over d. And so the moral of the story here is that this is another, and the same analysis works for mirrors. So the moral of the story here is that, for instance, with a telescope, I had alluded earlier that the most important thing was having a large diameter telescope, because you could get whatever magnification you wanted by dropping in whatever focal length eyepiece hit your fancy. But now we've got an additional issue, and that is that the wider the objective lens or the objective mirror, the lens if you're talking a camera, a mirror if you're talking a telescope, the smaller that these spots can go down to. Again, when you're designing a camera, that's typically not an issue unless you're doing very long-range telephoto lenses. You know, the sort that, say, people who are trying to take pictures of celebrities out in secluded locations might use. There, if they're wanting to get any kind of meaningful detail in the picture, not to mention gather more light, they're going to want a very large diameter lens. In fact, the lenses they use are so large that usually you mount the tripod to the lens because the lens is so much heavier than the camera. So this does have an effect on on being able to tell, for instance, whether you're looking at one source or two. So we call this resolution. So let's say you have a telescope that is trying to look at two very closely spaced stars. So here's one star, and let's say here's my other star coming in at some angle theta. How would we be able to tell whether or not they are resolved? Well, it turns out that there is a criterion due to Lord Rayleigh, so we call it Rayleigh's criterion, or A-Y-L-E-I-G-H, Rayleigh's criterion. And what Rayleigh argues is that if I follow through making the images of these, we can say that the images are just resolved if the central max of the one image, oops, sorry, didn't draw that very well at all, are just resolved if the central max of the one object sits right over the first minimum of the other. And for the system, that will also work out to be a and vice versa. So if we were to look at this sort of edge on, what you would get at this point is sort of a peanut-shaped kind of image where you could distinctly tell you're looking at two things. They're blurred together, but you could distinctly tell you're looking at two things. If these stars were any closer together, then this blur would get to the point where it'd lose this distinct little dent in the peanut shape here, and then you couldn't tell whether you're looking at one or two things. And obviously if the angle's bigger than that, then that dent in the peanut starts to go away and eventually just breaks away altogether. But in any event, you can definitely tell you're looking at two separate things instead of one. So, I mean, certainly you could use other criteria, but they're all going to come out to around roughly the same kind of idea. And so Rayleigh's criterion is the one that everyone pretty much uses. So what this means is that in order to resolve this, we're back to the angle having to be at least 1.22 lambda over d, where lambda is the wavelength of the light you're using and d is the diameter. So the way I'd like to think about it is that an image will be more highly resolved the more wavelengths of light that you could fit across the objective of the telescope or the camera lens. So as an example of this, if you go and Google search the Arecibo Radio Telescope, very, very large object. In fact, they can't even point it. It's that large, 100, on the order of at least 100 meters across. You would think it would have amazing resolution, but it's looking at radio waves that are in the centimeter wavelengths. So you're talking about fitting tens of thousands of wavelengths of light across that radio telescope. On the other hand, the pupil of your eye, even though it's just a few millimeters across, visible light is in the hundreds of nanometers. And so you're talking about fitting hundreds of thousands or so wavelengths of light across the pupil of your eye. So believe it or not, your eye in the visible has higher resolution than the Arecibo Radio Telescope does. So why do we bother building the Arecibo Radio Telescope in the first place? Well, that has to do with the fact that there is data that you can get in the radio that you can't get at other wavelengths. And so even though the image is poor compared to, say, what even your unaided eye could do, and that's for building a very large radio telescope indeed, it's still worth building it. There are tricks that astronomers do called very long baseline interferometry, or VLBI for short, or what they will do is when looking at, say, some distant radio source, they will coordinate observations from two radio telescopes on opposite sides of the Earth. And by very careful comparison of the two signals, they can reconstruct an image whose resolution would be the resolution of a hypothetical radio telescope, the width of the Earth. And so by doing that, they can get a lot better resolution. But this stuff is super tricky. If you read the papers for this stuff, you find that even during a few hour long observing period, they have to do things like take into account the continents drifting during the observation. So it is a very fussy thing indeed, but it is something that can be done to improve the situation for long wavelengths. On the flip side, you can get really good data looking at, say, the ultraviolet and stuff like that. Unfortunately, you pretty much have to put an observatory up in space to do that because our atmosphere does a pretty decent job of knocking out a lot of ultraviolet. Alrighty, so with that, thank you for having watched the videos in this course, and I hope to catch you all in cyberspace at some future date.